Dear students, I welcome you in this lecture on convergence of series of real numbers. This is our third chapter, series of real numbers, and the last topic in this chapter is convergence of series of real numbers. In this lecture, first we will understand few basics of series of real numbers that we have already studied. We will briefly recall them, and mainly we will see comparison test in absolute form for convergence and divergence of series of real numbers. So the first thing in basics that we are recalling is this: series an of real numbers is called series of non-negative real numbers if an is greater equal to 0 for all n belongs to I. So recall the basics that series an of non-negative real numbers is called series of non-negative real numbers if an is greater equal to 0 for every n belongs to I. Throughout this course, I denotes set of positive integers. In other words, series is of non-negative real numbers if every term of the series is non-negative. Then the series of non-negative real numbers is convergent if its sequence of partial sums is bounded. So, series of non-negative real numbers is convergent if and only if its sequence of partial sums is bounded. Let me repeat this result. It is very fundamental result which we often use. Series of non-negative real numbers is convergent if and only if its sequence of partial sums is bounded. This is a series of non-negative real numbers. This result in general is not true for other series of real numbers. This result is exclusively holds for series of non-negative real numbers only. A very fundamental fact which we often use is the result which I have stated. It is the series of non-negative real numbers is convergent if and only if its sequence of partial sums is bounded. Let us see the third result. This notation that series an is less than infinity denotes the fact that series an is convergent. So this result or this notation denotes the fact that series an is convergent. Note that this result is exclusively for series of non-negative real numbers. So this result is exclusively only for non-negative real numbers. So this notation denotes the fact that series is summable or it is convergent. Series an is convergent. Note that this is a series of non-negative real numbers. So I repeat, this result holds only for series of non-negative real numbers. Another notation which we will see is the series an of non-negative real numbers equals to infinity. This notation denotes the fact that series an is divergent. It denotes the fact that series an is divergent. Okay, so let me scroll a bit and recall the notation that the series is convergent. So this notation which I am explaining is it is a convergent series. Okay, now the next result which we will see is if series an, the sixth result which we are studying, if series an of non-negative real numbers is convergent, then any partial sum is less than or equal to value of the series. So any partial sum is less than or equal to value of the series. Any partial sum is less than or equal to value of the series if it is convergent series of non-negative real numbers. So note that the non-negative, all terms must be non-negative, then only we can say that partial sum of any convergent series of non-negative real numbers is less equal to value of the series. If the series mod an converges, then we say that it converges absolutely. Then we say that it converges absolutely. Eighth result which we are recalling is that every absolutely convergent series of real numbers is convergent. Finally, if series converges absolutely, then series also converges provided an is series of non-negative real numbers, that is an is greater or equal to 0 for every n belongs to I. So with these basic facts, we are now in a position to study convergence and divergence of series of real numbers. We will study comparison test in absolute form in next lecture. Thank you.